this video, we're going to be breaking down the probability and statistics on paper. Number 1. A competitor in a throwing event has 3 attempts to throw a ball as far as possible. The random variable x denotes the number of throws that exceed 30 meters. The probability distribution table for x is shown below. Part A. Given that expectation of x is equal to 1.1, find the value of p and the value of r. Okay, so let's find the expectation of x using the table above. So we can say that our expectation of x is equal to 0 times 4 plus 1 times p plus 2 times r plus 3 times 0.15. And this is expectation of x is 0 times 4 is 0, 1 times p is p, plus 2r plus 3 times 0.15, that's 0.45. And we're told that our expectation is equal to 1.1. So we know that p plus 2r plus 0.45 is equal to 1.1. And let's move the 0.45 to the right hand side. So it becomes p plus 2r is equal to 1.1 minus 0.45. 1.1 minus 0.45, that's 0.65. 0.65. And then now you notice that we have an equation in terms of p and r. We can create another equation in terms of p and r by adding up all these probabilities and equating them to 1. Because in a discrete random variable, the sum of all the probabilities add up to 1. So this becomes 0.4 plus p plus r plus 0.15 is equal to 1. So 0.4 plus 0.15, that's 0.55, plus p plus r is equal to 1, which is p plus r is equal to 0.45. Okay, now we have two equations in terms of p and r, and we can solve the two equations simultaneously. Let's make p the subject of the formula here. So that's 0.45 minus r. Let's substitute that into our other equation. This becomes 0.45 minus r plus 2r is equal to 0.65. So this becomes minus r plus 2r, that's 2r minus r, so that's r is equal to 0.65 minus 0.45. So therefore r is equal to 0.2. And now let's evaluate p. P is equal to 0.45 minus r, and our r is 0.2. So therefore p is equal to 0.25. Okay, let's move on to part B. Find the numerical value of var of x. So the formula for var of x is summation of x squared p minus the expectation of x squared. So let's find summation of x squared p using our table. So summation of x squared p would be 0 squared times 0.4 plus 1 squared times p, which is 0.25, plus 2 squared times r, which is 0.2, plus 3 squared times 0.15. Let's punch that into our calculator. So that's 1 squared times 0.25 plus 2 squared times 0.2 plus 3 squared times 0.15, which gives us 2.4. So summation of x squared p is 2.4. We can go back to our formula for variance. var of x is equal to 2.4 minus our expectation squared. Our expectation is 1.1 squared. Therefore, var of x should be equal to 2.4 minus 1.1 squared, which is 1.19. And that's our final answer. Number 2. George has a fair 5-sided spinner with sides labeled 1, 2, 3, 4, 5. He spins the spinner and notes the number on the side on which the spinner lands. Find the probability that it takes fewer than 7 spins for George to obtain a 5. Okay, so let's define our variable here. X is the random variable. Number of spins until a 5 is obtained. So this until means that we're looking for our first success. So it means we're looking at a geometrical distribution, and we're told that it's a fair 5-sided spinner, so the probability of getting a 5 is a 1 in 5 chance, which is 0.2. And we want the probability that it takes fewer than 7 spins for George to obtain a 5. So we want the probability that x is less than 7. And here we could just evaluate x equals 6, 5, 4, 3, 2, and 1. But that would be too tedious and would take way too long. We can use one of the shortcuts. We can simply write our probability that x is less than 7 as the probability that x is less than or equal to 6, and we can use 1 minus q to the power 6 to find this. So this becomes probability that x is less than or equal to 6 is equal to 1 minus q. Q represents the probability of failure, so that's 0.8 to the power 6, which therefore becomes the probability that x is less than or equal to 6 is equal to, punch that into your calculator, that's 1 minus 0.8 to the power 6, and you get 0.738. 0.738. Now let's move on to part B. George spins the spinner 10 times. Find the probability that he obtains a 5 more than 4 times but fewer than 8 times. So now notice in this statement over here, they tell us that George spins the spinner 10 times. They have now fixed the number of trials. This means that this is no longer a geometric distribution, but rather it is a binomial distribution. So let's define our new random variable. So let y be the random variable, number of throws, or rather, let's do spins, number of spins on which a 5 is obtained. Okay, and we say this is a binomial distribution. So we know that y follows a binomial distribution. Our number of trials is 10. Probability of success is 0.2. And they want us to find the probability that y is between 4 and 8. So this is the probability that y equals 5, 6, and 7. Okay, so let's find that. probability that y equals 5, 6, or 7. We'll use the formula for binomial probabilities, which is in the MF19. So that's 10 choose 5 times 0.2 to the power 5 times 0.8 to the power 5 plus 10 choose 6 times 0.2 to the power 6 times 0.8 to the power 4 plus 10 choose 7 times 0.2 to the power 7 times 0.8 to the power 3. And let's punch this into our calculator and see what it gives us. Okay, 10 choose 5 times 0.2 to the power 5 times 0.8 to the power 5 gives us 0.02642 plus 10 choose 6 times 0.2 to the power 6 times 0.8 to the power 4. That's 0.00505 plus the final one 10 choose 7 times 0.2 to the power 7 times 0.8 to the power 3. That's 0.0007864. Let's add up the probabilities and we should get, this is 0.02642 plus 0.005505 plus 0.0007864, which is 0.0327, and that's our final answer. Number 3. A factory produces a certain type of electrical component. It is known that 15% of the components produced are faulty. A random sample of 200 components is chosen. Use an approximation to find the probability that more than 40 of these components are faulty. Okay, let's start by defining our random variable. Let x be the number of faulty components. And this follows a binomial distribution. So that's x follows a binomial distribution and n is 200 and our probability of success is 0.15. Here you notice that they've asked us to use an approximation. So at AS level, the only approximation we use is the normal approximation to the binomial distribution. So in this case, it means that we're using a normal approximation. So what we have to do is we have to find the NP first. So NP is equal to 200 times 0.15. NP, that's 200 times 0.15, which is 30. And we also have to find NPQ, which is 200 times 0.15 times 0.85, which should give us 25.5. So when we approximate to a normal distribution, it becomes x follows a normal distribution with mean NP and variance NPQ. So our NP we've already established to be 30 and our NPQ is 25.5. And now let's go back to the problem we're required to solve. We want to find the probability that x is greater than 40. Now remember that this 40 was defined under a discrete distribution. So now we're moving this 40 to a normal or continuous distribution. So it means we have to apply continuity correction. Since 40 in a discrete distribution is exactly 40, but in a normal distribution, 40 actually represents any value from 39.5 up to 40.5. So this means if we apply continuity correction, we're looking for values of x that are greater than 40, not inclusive of 40. So we want to exclude 40, so we're starting at 40.5. Okay, now let's solve. So let's standardize. That's probability that z is greater than 40.5 minus 30 over the square root of 25.5. This becomes the probability that z is greater than, let's punch that into our calculator, 40.5 minus 30 over root 25.5, and that gives us 2.079. Okay, let's draw our bell curve for this problem. So we want greater than, our 0 would be somewhere here, and we're looking at 2.079. this is z, 2.079, and we want this region over here. So that means that's 1 minus phi of 2.079, which is 1 minus, read off the value from the normal distribution tables in the MF19, that's 0.9812, and this simplifies to give 0.0188, and that's our final answer. Number 4. The heights in centimeters of the 11 players in each of two teams, the Aces and the Jets, are shown in the following table. Draw a back-to-back stem and leaf diagram to represent this information with the Aces on the left-hand side of the diagram. Okay, so the first thing that we need to figure out is the stem of our stem and leaf diagram. So our smallest value here looks like 164, and our largest value is 190. Okay, so that means we need a stem that will represent 160 up to 190. So what we can do is to use 16, 17, 18, and 19. So 16 will represent 160 and 19 will represent 190. So we have, okay, let's first draw the lines. And we are told that they want the Aces on the left. So we've got the Aces and then the Jets. And we have 16, 17, 18, 19. Okay, now let's plot. We've got 164 for the Aces, 166 for the Aces, 168 for the Aces, 169 for the Aces, and then we have 171, we have 174, and we have, that's all in the 170s, we have 180. So let's start with, we have 180, we have 181, we have two 182s, 182, and I'd missed this 173. Okay, so this would be 173, and 174. And that's all for the aces. Let's move on to the jets. For the jets, we have 166 and 168, so that's 6, 8. We have 170, 0. We have 174 and 174 again. And then we have 175. We have two 181s. And we have 188, two 188. And finally we have a 190. So I think that's everything. 1 2 3 4 5 6 7 8 9 10 11. 1 2 3 4 5 6 7 8 9 10 11. Okay, so that's our diagram, and we need to add a key. So our key is that if we have 170, 0, this represents 171 centimeters for aces and 170 for the jets. That's our key. So this would be our final diagram. Part B. Find the median and the interquartile range of the heights of the players in the aces. Q2. So we have 11 players, so our median position is 11 plus 1 over 2, which is equal to 6. So we want the 6th player for the aces. So that's 1, 2, 3, 4, 5, 6. So 173 centimeters would be our median. So this means that therefore Q2 is equal to 173 centimeters, and they want the interquartile range. The formula for interquartile range is Q3 minus Q1. So Q3 is 3/4 so Q3 is the upper quarter, and to find the position of the upper quarter, we're going to say 3/4 of 11 plus 1. So that's 3/4 of 12, which is equal to 9. So let's find the height in the 9th position. So 7, 8, 9. That's 181. 181. So we know that Q3 is 181. Let's just put it here. Q3 is 181. And now we need to find Q1. So Q1 is 1/4 of 12. 1/4 of 12 is 3. So let's find the height in the 3rd position. So 1, 2, 3. That's 168. So Q1 is 168. That means our interquartile range is equal to 181 minus 168, which is equal to 13 centimeters, and that is our final answer. Part C. Give one comment comparing the spread of the heights of the aces with the spread of the heights of the jets. Let's look at our stem and leaf diagram again. So here, if you look at the jets, I want you to notice how the range for the jets is actually larger than the range of the aces, since the aces only end up to around 182 centimeters, but the jets actually end up at 190 centimeters. So this means that the heights for the jets are more spread than the heights for the aces, and that will be our answer. So we're going to say that the range of the jets is higher than that of the aces. This means that heights of jets are more spread than those of aces. Okay, let's move on to the next question. Number 5a. The heights of the members of a club are normally distributed with mean 166 centimeters and standard deviation 10 centimeters. Find the probability that a randomly chosen member of the club has height less than 170. Okay, so let's state our distribution. X follows a normal distribution with mean 166 and standard deviation 10. And we're required to find the probability that the height of a random member is less than 170. So probability that X is less than 170. Let's standardize as probability that Z is less than 170 minus 166 over 10, which is probability that Z is less than, punch that into your calculator, that's 170 minus 166 over 10, which is 0.4. Let's draw a diagram of our bell curve over here. 0 is somewhere here, and we want 0.4. 0.4 is here, and we want the region to the left of 0.4. So that's phi of 0.4. Read off the value of phi of 0.4 in the normal distribution tables, and our final answer is 0.655. Let's move on to part 2. Given that 40% of the members have heights greater than h centimeters, find the value of h corrected 2 decimal places. So we're given that the probability that x is greater than h is equal to 0.4. Okay, so what we're going to have to do here is we're going to have to use the tables in reverse. We are given the probability, but we're going to end up needing the z value. So let's start by standardizing. If we are to standardize, this would become z is greater than h minus our mean is 166, our standard deviation is 10. Okay, so let's just sketch a bell curve for our diagram, and this is still equal to 0.4. So we want greater than 0.4, so 0 is somewhere here. A probability of 0.4 would be somewhere here. So we're saying this area, this shaded area, is 0.4, and the unshaded region is 0.6, and we want to find this z value over here. That z value is equal to h minus 166 over 10. So what we can do is to say arc phi of 0.6. The reason we're using 0.6 instead of 0.4 is if you look in your tables, you notice that the probability values start at 0.5. So we can't actually use 0.4 since it's less than 0.5. We won't be able to find our z value. So since both 0.6 and 0.4 will result in the same z value, we can use 0.6 to find our z value. So arc phi of 0.6, if you read from your tables, will give you a z value of 0.253. Okay, and now we can substitute z over here and solve for h. So we have 0.253 is equal to h minus 166 over 10, which becomes 2.53 is equal to h minus 166, which is h is equal to 166 plus 2.53. Therefore, h is equal to 1.168.53. That's our final answer. Part B. The random variable x is normally distributed with mean mu and standard deviation sigma. Okay, so we're given that x follows a normal distribution with mean mu and sigma squared. Given that sigma is equal to 2/3 of mu, or given that sigma is 2/3 mu, find the probability that a randomly chosen value of x is positive. Okay, so if the value of x is positive, then x must be greater than 0. So we're finding the probability that x is greater than 0. Let's standardize that z is greater than 0 minus mu, which is our mean, and we're given that sigma is 2/3 mu, so over 2/3 mu, and this simplifies to give, that's mu over 2/3, 1/2/3, which is 3/2, and that's 1.5. The mu's cancel out, so you end up with z is greater than 1.5. And if we sketch a bell curve, we're looking at, this is 0, and we want 1.5. 1.5 is somewhere here, and we want greater than. So that means 1 minus phi of 1.5, and that's 1 minus, read off the value from the tables, at 0.067, which results in 0.933 as the final answer. Number 6. Freddy has 2 bags of marbles. Bag X contains 7 red marbles and 3 blue marbles. Bag Y contains 4 red marbles and 1 blue marble. Freddy chooses one of the bags at random. A marble is removed at random from that bag and not replaced. A new red marble is now added to each bag. A second marble is then removed at random from the same bag that the first marble had been removed from. Part A. Draw a tree diagram to represent this information, showing the probability on each of the branches. Okay. So we have bag X and bag Y. So we're choosing one of the 2 bags at random. So there's a 1 in 2 chance of picking bag X and a 1 in 2 chance of picking bag Y. And then a marble is removed from random from that bag and not replaced. So the marble is either red or blue, and the chances of a red marble in bag X are 7 out of 10 and 3 out of 10 for a blue marble. Okay, then for bag Y, red, blue, the chances of a red marble are 4 out of 5, and for a blue marble 1 in 5. And then we're told that a new red marble is now added to each bag. Okay, so in this case, we've got red, blue. So if we picked a red marble on our first pick, it means that we now have a total of 7 red marbles left. We picked a red marble, so there were 6 remaining red marbles, but then they added a new red marble, so it means we're back to 7. So it's still 7 out of 10 here, and this is 3 out of 10. And then we have, if we pick a blue marble, it means there are 2 blue marbles that now remain. So we now have 2 blue, and they added a red marble, so it's now 8 red instead of 7. They added 1 more red marble, so it's now 8 red marbles left. So we have 8 over 10, and this is 2 over 10. And then let's go to bag Y. If you pick a red marble on your first pick in the red bag, it means that on our second pick we must have 4 out of 5. and then blue marbles is 1 out of 5. And then finally, if you pick a blue marble, it means you now have 0 blue marbles and you now have 5 red marbles. So there's a 5 in 5 chance of picking a red marble, which is a probability of 1, and there's a 0 in 5 chance of picking a blue marble, which is 0. And this is our tree diagram. Let's move on to part B. Find the probability that both of the marbles removed from the bag are the same color. Okay, so if they're the same color, we're looking at picking bag X and then 2 red marbles, or picking bag X and then 2 blue marbles, or picking bag Y and then 2 red marbles, or picking bag Y and then 2 blue marbles. Now let's read off the probabilities from our tree diagram. So that's half times 7 over 10 times 7 over 10, and then XBB would be half times 3 over 10 times 2 over 10. Okay, and then YRR would be half times 4 over 5 times 4 over 5. And then YBB would be half times 1 over 5 times 0. And let's punch this into a calculator and simplify. That's half times 7 over 10 times 7 over 10 plus half times 3 over 10 times 2 over 10 plus half times 4 over 5 times 4 over 5. The last one will give 0, so we don't need to include it. And this gives us 119 over 200, and that's our final answer. Let's move on to part C. Find the probability that bag Y is chosen given that the marbles removed are not both the same color. Okay, so this is conditional probability. The formula for conditional probability is probability of B given A is equal to probability of the intersection over the probability of A. So in this case, A is the given event, given that the marbles are not both the same color. So not same color is A, and then B is bag Y is chosen, Y is chosen, and the intersection would be Y chosen and not same color. Not same color. Okay, so let's start by finding the probability of A intersection B. So we want to pick bag Y, but we want the marbles not to be the same color. So that means we're picking bag Y, and we want red marble to be picked first, then a blue marble. So we're looking at Y, R, B, and then we also want Y, B, R. Y, B, R. Those are the two probabilities. So A intersection B is equal to YRB, which is half times 4 over 5 times 1 over 5 plus half times 1 over 5 times 1. Punch that into your calculator and you get half times 4 over 5 times 1 over 5 plus half times 1 over 5 times 1, which gives us 9 over 50 or 0.18. Now we need to find probability of A, and we said A is that they're not the same color. So in part B, we found the probability that the two marbles are the same color. So to find A, we could simply say probability of A is equal to 1 minus the probability that they are the same color, which is probability of A is equal to 1 minus 119 over 200, which is 0.405. So we say that the probability of A intersection B is 0.18, and probability of A is equal to 0.405. Now we can substitute into the formula for conditional probability, and that's 0.18 over 0.405, which simplifies to give, punch that into your calculator, you get 0.18 over 0.405, which gives us 4 over 9 as our final answer. Let's move on to the next question. 7a. Find the number of different arrangements of the 9 letters in the word Andromeda in which no consonant is next to another consonant. The letters D, M, N, and R are consonants, and the letters A, E, and O are not consonants. Okay, so what we can do, we want to make sure that no consonant is next to each other. So I'm going to use an X to represent the slots in which we can put the consonant such that they are not next to each other. So we can put an X here, and then we want the vowels. The vowels, we have A, and there's another slot. Then our next vowel is O, and there's another slot, and then our next vowel is E, then we have another slot, and then A, then we have another slot. And how many consonants do we have? We've got N, D, R, M, D. Let's just make sure that adds up to 9. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So these X's over here represent the slots that we can put the consonants so that none of the consonants are next to each other. So for the consonants, we have 5 consonants, and they can be put into the 5 slots which are being denoted by X over here. So that's 5 factorial. But notice that we have 2 consonants that are the same, that's D and D, so we have to divide by 2 factorial, multiplied by, now let's find the arrangements for the vowels. We have 4 vowels, so that's 4 factorial, and we have 2 vowels that are same, that's the letter A's, and that's 2 factorial. If you simplify that, that's 5 factorial over 2 factorial times 4 factorial over 2 factorial, which gives 720. So the total number of arrangements are 720 arrangements. Let's move on to part B. Find the number of different arrangements of the 9 letters in the word Andromeda in which there is an A at each end and the D's are not together. Okay, so we want A at each end. So that's A at each end, A at ends, and D is not together. D is not together. What we can do to get this is we can say the total number of arrangements where we have A at the ends and there are no other restrictions minus the total number of arrangements where we have the A's at ends and the D's are together. D's together. if we subtract A at n's and d's together from A at n's, we should get A at n's and d's not together. So let's start by finding the number of arrangements in which the a's are at the n's and the d's are together. So we've got our letter A here, and then we want our d's to be together. What other letters do we have? We've got N, we've got R, O, M, E, 1, 2, 3, 4, 5, 6, 7, 8, and then we have another A there. Okay, so our D's are together, we're not rearranging the A's, so what we are actually rearranging are the items that have underlines. So that's 1, 2, 3, 4, 5, 6 items are being rearranged. So that's 6 factorial. 6 factorial, which gives us 720. So this is 720. Now let's find the number of arrangements where the A's are at the ends and there are no other restrictions. So that would be, this would look like this. This would now be D and D. It's now, we're rearranging now 7 items. So that's 7 factorial, and then the d's appear 2 times. So we divide by 2 factorial. So 7 factorial over 2 factorial is 2520. 2520. So going back to our expression, that will be 2520 minus 720, which gives us 1800, and this would be our final answer, 1800. Let's move on to part C. 4 letters are selected at random from the 9 letters in the word Andromeda. Part C, find the probability that this selection contains at least one D and exactly one A. Okay, so let's create an expression for our probability. We're looking at least one A, at least one D and exactly one A over, that's the total number of selections, total selections. That's how we'll get our probability. So what we have to do is to find the number of scenarios where we have at least one D and exactly one A. So that can be 1D and 1A, or that could be 2 D's and 1A. So these are the 2 possible scenarios. So that would look like we've got an A, we've got a D, and we've got 2 empty slots since we're picking 4 letters. And the second one is we've got an A and we've got 2 D's and we have 1 remaining slot. So to pick an A in the first scenario, that's 2 choose 1, times to pick a D, that's 2 choose 1 as well. And if we remove all the A's and D's from the selection, only 5 letters remain. So we have 5 letters remaining for these final 2 slots. So that's 5 choose 2. And if we simplify this, that's 2 times 2 times 10, which is 40. And then the second scenario, to pick one A, that's 2 choose 1. To pick 2 D's, that's 2 choose 2. And we have 1 remaining slot for 5 letters, so 5 choose 1, which is 2 times 1 times 5, which is 10. If we add up the 2 scenarios, we get 50. So the total selections, when there are no restrictions, we have 9 letters for 4 slots. So that's 9 choose 4, which is 9 choose 4, 126. So if we are to go back to our expression, This would then become 50 over 126. And if we simplify that further, that's 25 over 63. So our final answer would be 25 over 63. So that's our final question. If you enjoyed this video, please like and subscribe for more videos like this, and comment down below which paper would you like to see me break down next. Bye bye.